Okay, yeah, good morning everyone. Welcome to the talk. So I'm going to be talking today about GPU performance portability using standard C++ with SYCL. So first, a quick show of hands. Who here is programming for GPUs or who has programmed for GPUs? Okay. What APIs are you using? Cocos? Okay. Anyone using CUDA? CUDA? Okay. Uh-huh. Vulkan? Okay, graphics, yeah. Okay, anyone using OpenMP? Any SYCL users? Yeah, well done, okay. Yeah, so I'm going to be talking about SYCL and why SYCL is great, especially in terms of performance portability. Okay, so first a quick word about my company. So I work for CodePlay. So we developed the first SYCL implementation called Compute CPP. This was a few years ago when SYCL was an OpenCL abstraction layer for C++. It's now developed into something a lot bigger. We also have our own OpenCL implementation, Compute Aorta. Yeah, and we work with lots of hardware companies. People would come to us with a chip, and they want essentially our software stack to enable, say, SYCL or OpenCL on that chip. We also work with a lot of, with the national labs, people who have kind of big hardware requirements. They want to run SYCL for the reasons, and OpenCL as well, but it's moving towards SYCL for the reasons that I'll talk about. As well, at any point in the talk, if you have a question, please interrupt. Same as online, if you have any questions, just cut across me. I'm more than happy to answer any questions. Also, so we work with Intel. We were recently acquired by Intel, so we're now a wholly owned subsidiary of Intel just in the last few months. What about me? So I work on the CUDA backend of the DPC++ SYCL compiler. Okay, so this is an open source implementation of SYCL. It's spearheaded by Intel, but it's an open source implementation. You can contribute if you want to take part. You can see it on GitHub. Recent work. So adding support for the C++ standard library for the CUDA backend. Also adding support for the TF32 data type for the DPC++ join matrix API. So this is enabling very, very new kind of cutting edge features that are enabled in the CUDA API. We're adding this as an extension to DPC++. So you can do these things through SYCL that are specific to individual hardwares like CUDA. What about you? Okay, who are you and what do you want? So I'm guessing that you're a C++ developer or enthusiast. I'm guessing that you want to use standard C++, or you are already using standard C++ for hardware acceleration on GPUs or other devices being DSPs, FPGAs, and so on. You want the guarantees that open standards provide, okay? Open standards provide guarantees in terms of portability, in terms of compatibility, interoperability, all these things. We want these when we're developing our code bases. And you want the flexibility to run single source code on whatever accelerators you have at hand. Okay, you want to be able to write code once and run it anywhere. This is a really, really powerful thing about the SYCL API and the DPC++ implementation as well. And most importantly, you won't compromise on performance. You won't trade performance for this portability. Okay, and that's what this talk will be about. So you need SYCL. Why? So SYCL is a C++ interface enabling heterogeneous acceleration. So SYCL here is down the bottom. Down here, I'm not sure if that's visible. Okay, it's pure C++. Looks like a library within C++. You don't have to learn any funny pragmas, any kind of double underscore notation, all this kind of stuff. It's an open standard under the Khronos group. Okay, that means that if you want to take part in the discussion about the language, in the direction of the language, you can make suggestions to the working group and contribute in that way. You also have some guarantees in terms of interoperability, compatibility, and so on. So if there's something that isn't supported by the SYCL API, interoperability with other APIs is very well defined, so you could potentially call CUDA kernels from your SYCL code and so on. And SYCL can be used to run single source code on AMD, Nvidia, or Intel GPUs and more. So this talk is primarily about GPU programming, but it can run on anything, okay? Well, if an implementation supports that, yeah. and performance of SYCL code is comparable to the performance of native APIs. Okay, so this talk will hopefully demonstrate that. Okay, so quick overview of the SYCL implementations. Okay, so here we have, okay, Compute CPP. This was the first SYCL implementation, which is developed by my company, CodePlay. It started as an OpenCL kind of C++. Oh dear, what has happened? Okay. Pause. Let's do. Okay, from current slide. Okay, sorry about that. Yeah, so Compute CPP started as an OpenCL abstraction layer for C++. Now it's developed into something a bit more. We have an experimental Nvidia OpenCL backend, as you can see here. So I work here on the DP++ implementation. So again, it's open source, but it's spearheaded by Intel. I work specifically on the CUDA backend. And you can see that this is a quite well-developed implementation. We have lots and lots of different backends, including Intel GPUs for level 0, Nvidia GPUs, as well as AMD GPUs, as well as anything that can consume SPIR-V, so things like Intel FPGAs, Intel CPUs, GPUs, and so on. SYCL is a kind of research project developed by the University of Heidelberg, also very interesting. They're doing a lot of interesting experiments with SYCL and how it can be implemented. It's a bit unique in that it didn't start off with an OpenCL backend, which the other ones did, so it's a bit unique. Okay, so what does SYCL look like? So, in short, it looks like just normal C++. Okay, it looks like maybe you're using some sort of a library in C++. We have these buffers and accessors. I won't get into how they work, but this is a really nice feature of the SYCL language that abstracts away things like data migration as well as dependency management. This is a really, really nice feature of the SYCL language that you don't necessarily get in other APIs. Here we have our device code. So you can see that we're just doing a simple kind of vector square operation on device, on GPU. Okay, so again, modern C++. So it uses exceptions, lambdas, templates, CTAD, all these things. So a quick disclaimer. So exceptions usually aren't supported within device code, but the SYCL API can deal with error messages from device through exceptions. We allow these errors to be propagated through exceptions. So it fits nicely within your existing C++ code base, your modern C++ code base. Okay, and again, it's single source. Okay, so there's no separate translation unit for your device code as well as your host code. This is a nice thing. It allows it to be more readable, and you only need one compiler, which is your client compiler. Not a general compiler, but say a DP++ client compiler or Compute CPP compiler and so on. As an aside, because it's just standard C++, library-only implementations are possible. So SYCL has done some interesting experiments with enabling SYCL as a library for the Nvidia C++ compiler. Okay, so this is a potential future of SYCL as library kind of implementations. And yeah, feel free to experiment on Godbolt. Okay, so this is using the Intel C++ compiler. You need to use the kind of the modern one, and this is with the fSYCL flag. Yes.
How would you do a library on the CUDA?
For CUDA, so if you use the NVCC compiler, so I went to this talk that Axel gave, but I wasn't involved in this at all. But essentially, this can be the details. It just works as a standard library in CUDA. It works in the same way that, say, I don't know, cuBLAS or CUDA. Say again?
You would need the annotation.
You need the annotations, yes, exactly. Yes, but this would be provided by the compiler, or it would be. So these experiments, they're not supported.
But your SYCL code without annotation wouldn't compile with that.
SYCL code without annotation? When you say annotation?
It wouldn't work, right? Because it's not annotated.
When you say annotated, what do you mean?
Host device.
Host device. No, sorry. Okay, so you would compile this as C++ using not NVCC, using NVC++, and then this is just standard C++, and then the library would figure out how to, target the CUDA kind of runtime. So, I'll link you to this talk that Axel gave. It's totally possible to implement this using the Nvidia C++ compiler. Okay, and yeah, experiment on Godbolt, please. This is a little bit limited in that it's only enabled for CPU backends at the moment, but yeah. Okay, so how does the DPC++ toolchain work? So essentially, we take our kernel code, we pass it to, and we generate device code for any particular backend. This is just using flags that we would pass to the compiler at compilation time. The device code is then bundled within the final binary, and then at runtime, this is dispatched to the device, and we can have multiple bundles within the same binary. This is quite a nice thing. Okay, so some quick compilation in action. Okay, so here we have, we have our SYCL code. Okay, here we have our buffers and accessors. Oh dear me. Okay, and accessors. Okay, here's our parallel for. So this is our device code here. We're just doing our vector square. Okay, so we can do. Okay, so here we're compiling for the CUDA backend. Okay, and we see that this generates CUDA assembly PTX. Okay, and if we scroll down, we can see that we have our loads, our moles, and our stores. Okay, so this is just our assembly for CUDA. Okay, and without changing anything, we can also compile for Spear. Okay, so SpearV, this can be used to run on Intel FPGAs, Intel CPUs, lots of different things, also level 0 GPUs. Okay, here we have our Spear. So we haven't made any changes at all to the code, okay, and it can run on, it can be compiled for lots of different backends, and these will be bundled within the final binary. We can compile as well for multiple targets at the same time, in the case that we want to produce a very, very generic binary. Okay, so we'll close that, okay. So now let's have a look if we run this. Okay, so we can see that we're running on the device, the Intel graphics, okay, and the vector sum runs in say, whatever. Okay, we can see, so what devices are actually available to us on this, on my laptop. So we have our level 0 graphics, as well as the host platform. So if we want to, we can take this exact same binary, and we can run it as well on the host. Okay, and then we run on the host, exact same result, and the vector sum runs in slower. This is a really, really nice thing. I can develop code on my laptop where I don't have, say, a CUDA GPU, and later deploy that exact same code to, my workstation, my server, where I'm running it on a CUDA GPU. And this is great for debugging as well. We're able to debug on host, which is just normal C++ compiled code. Okay.
From online, does it make it a fat binary? Are there implications for this?
It does make it a fat binary, yes. So there are some implications. So say the PTX, the CUDA assembly that's generated is bundled as plain text within this binary. There are some concerns about things like reverse engineering, but things can be reverse engineered in exactly the same way with most of these APIs. So it's not different in that way. It is quite, it's a relatively large binary. If you compile for a lot of different backends at the same time, your binary will get bigger. But you're going to need some device code to be bundled within this binary anyway, regardless of the API that you use. Okay. Okay, so back to the slides. Yeah, so there's some compilation in action. Okay, so a word about specialization and abstraction. Okay, so in general, intuitively, we understand these concepts, specialize being more specific to a particular device, particular API, particular backend, and so on. Abstraction being more generic, okay? So some examples of specialization. So writing code for a specific architecture, if we're writing code for GPUs, we're going to use the GPU programming kind of paradigm. Okay, we're going to use certain types of memory. We're going to think about how GPU code executes. In say, I won't get into this in detail now, but we think like a GPU. Okay, and this is a specialization as well, because if we write our code thinking like a GPU, we cannot expect it to run, or at least run well, on a CPU. Okay, another example of specialization is writing code using vendor-specific APIs like CUDA. Okay, this is an example of specialization, because if we write our code in CUDA, we lose the ability to run our code on, say, AMD GPUs, on Intel GPUs. There are tools to convert, say, CUDA to HIP, which can run on AMD GPUs, but this is it's not a laborious process, but it's not necessarily an easy process. Well, maybe it's not the worst, but you cannot do that for Intel GPUs, say. As well, another example of specialization, optimizing code for the specific features of a particular device. We might be optimizing device code, but knowing that we want our cache line to be totally optimized, adding offsets, all this kind of thing. We want to be filling this particular part of memory to the brim so that we can really, really squeeze every inch of performance out of our code. This is an example of specialization where we're using this to get high performance. We can expect it to translate well to other backends, other devices, and so on. Examples of abstraction. So using APIs that map to different backends, such as SYCL, OpenMP, as well. Cocos is another example. Yeah, this gives us a lot of flexibility. We can write our code once, run it anywhere. This is great. Using libraries that support multiple backends. So these are some one API libraries. So these libraries take care of the specialization that enables high performance, okay? You deal with a very, very abstract interface, and this can run for multiple backends. As well, allowing an API to abstract away details of data transfer and heterogeneous execution. So I know I very briefly mentioned it, but the buffer accessor model in SYCL is a really, really great feature of the language that abstracts away a lot of the messy stuff that trips us up when we're programming for GPUs, like dependency analysis, like data migration. We don't have to use it. There are alternatives. We can use pointer-based approaches like are used in, say, CUDA, but this is a great feature of the language. We really, really like this. Okay, benefits of specialization, optimization, okay? As well, if we're using proprietary APIs like CUDA, we can be guaranteed that we have access to the absolute latest features in CUDA, which maybe you can't get through DPC++ extensions, but usually they are added, albeit at some time later. Benefits of abstraction, code portability, they increase your productivity. Okay, you don't need to necessarily get into the nitty-gritty if you're using these higher-level abstractions. We don't need to learn platform-specific APIs. This is especially important if in our work we need to deal with lots of different platform-specific APIs depending on your work. And in general, we understand that specialization corresponds to more programming effort, lower productivity. Okay, it's usually more difficult to program in a very, very specialized way and squeeze performance. Abstraction corresponds to less programming effort, higher productivity. Okay. Now, I'm going to present this specialization and abstraction axis versus another axis, but caveat, this is not a numerically precise scale. For a precise presentation, look at the Pennycook and Deacon talk, or paper at least. Okay, so here we have our axis of specialization and abstraction and optimization and regression on the Y. Okay, this is the absolute dream. Okay, if I can write the most generic code without caring about the hardware, without caring about the underlying API, and if I can get full optimization, then this is, why do I ever need to learn anything hard? Again, this is a dream because it's not realistic. Okay, the natural correlation is between optimization and specialization and regression and abstraction. Okay, so if we're moving along our abstraction specialization axis, if we're moving, say, left on this axis, we want to make sure that we're also moving up. If we're not moving up, then that's a problem. Okay? In general, the more specialized our code, the more optimization we should expect, but we should not accept greater specialization unless it offers greater performance. Okay? So some examples. So writing generically parallel code. It's relatively abstract, or the most abstract in this case. Again, not numerically precise, more notional. Writing generic GPU code, if we're being more aware about how GPUs execute code and so on. This is more specialized. We can't expect it to transfer to other devices and so on. the paradigms. Writing GPU code in vendor-specific APIs, this is more specialized because we can no longer run this code on other vendors' GPUs. And the most specialized is writing GPU code that takes advantage of specific hardware features, highly optimized code. This is very specialized. We can't. Yes, question?
Oh, is there a CPU backend as well? For example, testing on headless continuous integration servers that don't have GPUs?
Yeah, absolutely. Yeah, so this can run. You can run it on host, which is just C++. It's just compiled for normal C++. You can also run on OpenCL CPUs. Yeah, you can run it on any CPU. All of the SYCL implementations support CPU multi-threading and so on. Okay. Okay, so we can see here that we're moving along the optimization scale, but writing code in vendor-specific APIs, we're getting more specialized without necessarily gaining performance. Okay, so this is a problem. We don't want to sacrifice our portability, our abstraction, without getting more performance. So this is a problem. But the question is this justified? Can generic GPU code written in SYCL really perform the same way as, say, CUDA code? So a few quick comparisons. Okay, so this is Babel string. So these are very, very simple kernels. So comparing CUDA, SYCL, and OpenMP, the code that's actually running on the device is probably very, very, very similar because the kernels are, the device code is so, so simple. So this gives us a nice estimate of the overhead of using the SYCL runtime. And we can see that it's totally comparable. Okay, another comparison. This is using a kind of a few micro benchmarks on HipSYCL. Okay, we can see that the performance again is comparable for HipSYCL as it is for CUDA. Optimized CUDA being in the middle, blue, HipSYCL being red. Higher is better. So comparable performance again. And now for a truly massive code base, so LAMMPS being a molecular simulator, which is hundreds of thousands of lines of code, or maybe 800,000 lines of code. Again, CUDA slightly edging in performance, but we gain a lot for that. We really, really gain a lot. Yeah, and this is running on multiple GPUs as well. Okay, so this is a good thing. Yeah. Okay, so when you're writing CUDA code, you're essentially writing code in this box. Okay, you're able to get highly specialized if you want, but you're limited by your ability to write abstract code. Okay, you're tied to your particular vendor. You're locked in by that. And also you don't have the same features that SYCL provides, these abstract features, like the buffer accessor model. Also, we can express very generic parallelism in SYCL, which I perhaps don't have time to get into right now. Okay, so with SYCL code, as we've seen in the benchmarks, we can get up here if we want to. Okay, maybe it's slightly off, but we can get up here. But we can also get all around here. Again, not numerically precise, more notional, but we can write generic parallelism, okay, which gives very, very high productivity. It's as easy as writing a for loop. We don't need to care about particular features of the hardware, and this will port very, very nicely between different backends. We can write SYCL code for GPUs, which is more abstract than CUDA code for GPUs, and achieve comparable performance. And we still have access to this high realm of specialization optimization. And moreover, we can choose where we want to be in this plane. We can choose if we want to have this part really, really squeezed and optimized, and this part more abstract if it's not as compute intensive. And the degree of specialization or abstraction can vary throughout a code base. We can write some parts that are highly, highly optimized, other parts that we don't need to be highly optimized. So in reality, most code will be written here, potentially, or some code will be written here, highly productive, easy as writing for loops, and we're prioritizing our programmer productivity over performance. And then when we want to, we can optimize to the hilt these hot parts of our code base, okay? And this is why SYCL is being used on all of these supercomputers, because you can write your code where you have high degrees of optimization in some very, very hot parts of the code base, but a lot of it as well, you're prioritizing your portability, your programmer productivity over that. And these can port relatively easily You'll still need to specialize if you want to squeeze your hot kernels for performance, but you have the option of where you want to choose specialization versus abstraction. You have the choice. Okay, so the takeaway, with SYCL, you can use modern C++. You can write code that can target multiple architectures, platforms. You can attain comparable performance to the native APIs, such as CUDA. And you can choose how generic or specialized your code ought to be. And this can be a decision that you make on the fly. Every part of your code, you can say, I don't need performance here. Let's prioritize my productivity, and so on. Okay, questions?
So I have a question regarding interoperability.
Yeah.
Can you go back to slide 18? So in slide 18, you were showing how you could get something very specialized, but that would be written in SYCL code.
Yes, it is.
How would you go about if you needed to use some, let's say legacy code that's written in CUDA, but you opt to code because it's, you don't want to rewrite it.
Yeah, of course. So that you can use SYCL interoperability with CUDA, where you're calling CUDA code from SYCL. Okay, this is using host tasks. We also have tools to convert to port CUDA code, legacy CUDA code, to SYCL. You don't have to use them. You still need to tweak them a bit, but interop is your friend.
So you can get a stream out of a queue, and you can...
Yes. You can do anything that you can...
Construct a queue around the
stream. No, you cannot construct a queue out of a stream. The interoperability is it's kind of more mutually exclusive. You can't mix and match the two APIs in as clean a way. You can call CUDA kernels from SYCL, but I think with streams and constructing queues, you cannot do that. Yeah. Okay, thank you. Hey.
So the idea of having different sort of what looks like C++ library code for running GPU or device stuff on different backends. It sounds quite similar to Cocos. So what would you consider to be some of the major differences?
The major differences of Cocos. Okay, so I admit I'm not an expert on Cocos. So I think one of the great things about SYCL specifically is the buffer accessor model. This abstracts away a lot of details that we don't necessarily want to worry about, like data migration and dependency analysis. I'm not sure in terms of interoperability, perhaps Michael can...
We have the Cocos expert here who would be able to know that. But there's, Cocos has more things about layouts and placement of data. So that's where some of the difference. And we're bringing that into SYCL through C++. But Cocos devises a framework that can dispatch to many different things, right? Like OpenMP, OpenACC, as well as CUDA and SYCL. So we have the expert here who can probably answer that question. Yeah, go for it.
Yeah. Okay, thank you.
Maybe really quick from online, how would you compare SYCL to other cross-platform compute libraries like Vulkan Compute?
Vulkan Compute. So SYCL we usually think of in terms of so Vulkan is a graphics API. We don't think of SYCL as a graphics API. We think of it as a compute API. That being the main difference. I think you could probably do a lot of what you do in Vulkan in SYCL, but it seems that these worlds are a little bit separate. Yeah.
And just to answer the question from earlier, right? One difference is that Cocos is a library-only solution which targets each vendor's primary compiler chain. Right? So you're not, if you're on AMD GPUs, you use AMD's compiler. If you're on Nvidia GPUs, you use Nvidia's compiler. If you're on Intel's GPUs, you're using Intel's compiler, right, from the beginning. The other thing is that the buffers, you mentioned that as one of the great things about SYCL. It's also one of the Achilles heels, right? Because they really don't interact well with classes and having private data structures. Mm-hmm. Because you have to get the accessors out, in the submit thing. Mm-hmm. And if you have a class which owns buffers, right, which are private, you have no access to these guys.
Okay.
I mean, they fixed that with supporting raw pointers and essentially doing what they call the USM thing. And so you can now use pretty much mallocs, right, to build higher level data structures, and that fixes most of these issues, for us at least.
Yeah. So USM as well has been a core SYCL feature since SYCL 2020. So things that you cannot do with the buffer accessor model, you can do with USM with a more pointer-based approach. Time's up, but thank you very much.